Welcome, everyone. Today, we are going to gently explore a foundational concept in mathematics. We will be understanding N choose R, walking through a visual, set-theoretic guide. Take a deep breath, relax, and let's visualize the beautiful logic behind combinations. You might be asking yourself, why should we care about this? The truth is, combinations appear everywhere in our real, everyday lives. Think about it. How many ways can you pick 3 delicious toppings from a menu that offers 8? Or if you are playing a game, how many different 5-card poker hands can be dealt from a standard deck of 52 cards? Imagine you're at school or work. How many distinct committees of 4 can be formed from a class of 30 students? There's a crucial pattern in all these examples. The order simply does not matter. Picking Alice and then Bob gives you the exact same committee as picking Bob and then Alice. It's the group itself that counts, not the sequence. Before we dive deeper, let us establish a color code to help our visual understanding. Throughout this presentation, specific colors will carry specific meanings. Whenever you see the letter N, remember that it represents the total number of items available to us. The letter R represents the exact number of items we want to choose from that total. The capital letter S stands for the set, which is simply the collection holding all of our items. Finally, the mathematical notation N choose R represents the final answer, the number of ways to choose our items. Let us begin with part 1. What exactly are combinations? To answer that, let us meet the set. Imagine our set, S, contains exactly 4 distinct items, meaning N equals 4. We can write this mathematically as set S equals the collection of A, B, C, and D. Now, what is a set? In mathematics, a set is simply an unordered collection of distinct objects. Because it is unordered, the set of A, B, C, and D is exactly the same as the set of D, C, B, and A. The order in which we list them inside those brackets does not change the set itself. Order does not matter. Now, let us try making a choice. Suppose we want to choose exactly 2 items from our set, so R equals 2. Look at our 4 items. One possible choice would be to pick item A and item C. When we pull those out, we get a smaller group called a subset containing just A and C. But pause for a moment and ask yourself, is this the only way we could possibly choose 2 items from our group of 4? The answer, of course, is no. Let us visually list all of the possible choices. The expression 4 choose 2 is essentially asking a specific question. How many distinct groups of size R can we form from our N items? Let us find out by listing every single way to choose 2 items from our set of 4. We could pair A with B, we could pair A with C, we could pair A with D. Moving on, we could pair B with C or B with D. Finally, we could pair C with D. If we count them all up, we see there is a total of 6 distinct pairs. Therefore, we can confidently conclude that 4 choose 2 equals exactly 6.
Let us take a look at the complete picture for our set when n equals 4. We can organize every possible group size, R, from our set of A, B, C, and D into a clear row-by-row table. Starting at the very top, when R is 0, meaning we want to choose absolutely nothing, there is exactly one way to do that, the empty set. So 4 choose 0 is simply 1. Moving down, when R is 1, we can choose A, B, C, or D individually, giving us a count of 4 ways. We already discovered that when R is 2, picking pairs gives us 6 distinct combinations. If we increase R to 3, creating groups like A, B, and C, or B, C, and D, there are exactly 4 ways to do this. Finally, if R is 4, meaning we want to choose all the available items, there is only one way to do it. we just take the whole set. Notice a beautiful mathematical pattern here. If we add up the totals across all these rows, 1 plus 4 plus 6 plus 4 plus 1, we get 16, which is exactly 2 raised to the power of 4. Also, as a quick rule of thumb, if you try to choose a negative number of items or more items than you actually have, it is logically impossible, so the answer in those cases is always 0. Now that we have seen the visual patterns, let us transition to Part 2, Deriving the Formula. How do we calculate these numbers without having to draw out a table every single time? To discover the formula, we first need to clearly understand the difference between permutations and combinations. As we saw in our table, a subset like A, B, and C is counted as just one single group. For a combination, which we write as n choose R, the order simply does not matter. Choosing A, then B, then C creates the exact same team as choosing C, then B, then A. However, for a permutation, written as NPR, the order absolutely does matter. Think of a digital password. The password ABC is completely different from the password CBA. To find our combination formula, we will first figure out the permutations, and then logically remove the extra groups we overcounted. Let us clearly see this overcounting in action. Imagine we want to choose 3 items from our total of 4. Look at this grid. Each column represents just one distinct subset. For example, the first column is the subset containing A, B, and C. But look closely at the rows underneath that heading. They show every possible way to rearrange those exact same 3 letters. We have ABC, ACB, BAC, BCA, CAB, and CBA. That's 6 different arrangements or permutations for just one single subset. If we expand this logic to all 4 distinct subsets, we end up with a total of 24 permutations. Even though we have 24 permutations, we still only have 4 truly distinct subsets. Because 3 items can be arranged in 3 factorial ways, which is 3 times 2 times 1, or 6, we can clearly see that each unique subset has been overcounted exactly 6 times. This brings us to what we call the 2-step principle. Generating permutations is really just a logical 2-step process. Step 1, you choose your R items. The number of ways to do this is our combination, n choose R. Step 2, you arrange those specific items you just picked. The number of ways to arrange them is R factorial ways. Therefore, the total number of permutations, NPR, is equal to the combinations, n choose R, multiplied by R factorial. Looking back at our grid, those 24 total permutations were simply the 4 distinct groups multiplied by the 6 different ways to arrange each one. Now we are completely ready for deriving the formula. We start with the simple equation we just built. Permutations equal combinations multiplied by R factorial. Since our goal is to isolate and find the combinations, we simply divide both sides of the equation by R factorial to mathematically remove that overcounting. This gives us a new equation. N choose R equals NPR divided by R factorial. We already know from standard algebra that the permutation formula NPR is n factorial divided by n minus R factorial. When we gently substitute that into our equation, we arrive at our beautiful final formula. N choose R equals n factorial divided by the product of R factorial and n minus R factorial. Let us put this wonderful formula to the test with a worked example. Let us verify our new math against the simple example of 4 choose 2, which we listed out manually at the very beginning. Plugging our numbers into the formula, we get 4 factorial on the top numerator. On the bottom denominator, we have 2 factorial multiplied by the quantity of 4 minus 2 factorial.
This simplifies down to 4 factorial divided by 2 factorial times 2 factorial. If we expand those factorials out, the top becomes 4 times 3 times 2 times 1, which equals 24. The bottom becomes 2 times 1 multiplied by 2 times 1, which equals 4. Finally, 24 divided by 4 gives us exactly 6. The mathematics perfectly matches the 6 subsets we intuitively counted by hand.
Now we move to part 3, where we will gently uncover some of the key properties of combinations. Let us begin by looking at what we call the binary view. It turns out that every single subset can be perfectly encoded as a simple binary string. In this view, a number 1 means an item is chosen, and a number 0 means it is not chosen. Imagine our 4 items, A, B, C, and D. If we write the binary string 1010, it perfectly represents the subset containing just A and C. Each unique 4-bit string corresponds to exactly one subset of our main set. Because there are 4 positions, the total number of binary strings is 2 to the power of 4, which equals 16, representing all our possible subsets. So calculating 4 choose 2 is exactly the same as counting the number of strings that have exactly 2 ones, which gives us 6. This brings us to a beautiful concept called symmetry. The mathematical rule states that n choose r is always equal to n choose n minus r. Think about it this way. Every single time you choose r items to keep, you are simultaneously leaving behind exactly n minus r items. For example, when we chose our 2 items, A and C, we automatically left behind the other 2 items, B and D. There is a perfect one-to-one match between the groups we keep and the groups we leave out. Choosing r items to keep is mathematically identical to choosing n minus r items to leave out. This provides a wonderful practical shortcut. Instead of calculating 100 choose 98, you can simply calculate 100 choose 2, which quickly gives you 4,950. Now let us review some important boundary and special cases. First, n choose 0 always equals 1, because there is only one way to choose nothing, which is the empty set. Second, n choose 1 equals n, because picking each item alone is a valid choice. Third, n choose n equals 1, as there is only one way to just take everything. Fourth, n choose n minus 1 equals n, which is the exact same logic as choosing one item to leave out. Finally, if r is greater than n, the answer is 0, because you cannot choose more items than exist, and if r is less than 0, the answer is also 0, because you cannot choose a negative number of items. Let us gracefully transition into part 4, where we will discover Pascal's identity and his famous triangle. We start with Pascal's identity using what we call the star argument. This provides a beautiful recursive way to compute combinations. The mathematical formula states that n choose r equals n minus 1 choose r minus 1 plus n minus 1 choose r. To visualize this, let us single out one special item from our set and call it the star. From our items A, B, C, and D, let us say item A is our star. This leaves items B, C, and D as the remaining n minus 1 items. Now, every possible subset must either include this star or exclude it. Let us look at case 1, where the star is included in the group. If we definitely include the star, then one of our available slots is already filled. This means we now only need to choose r minus 1 more items from the remaining n minus 1 items. Visually, item A fills the first slot, leaving the next slot with a question mark, representing that we need r minus 1 more. Mathematically, this is n minus 1 choose r minus 1. For example, if we needed a pair and A is already chosen, we just need to choose 2 minus 1, or 1 item, from the remaining set of B, C, and D. 3 choose 1 gives us exactly 3 possible groups. Now, let us consider case 2. The star is out of the group. If we completely exclude our special star item, then all R of our slots remain empty. We must carefully fill all R slots strictly from the remaining n-1 items. Visually, we see question marks for all the slots we need to fill. Mathematically, this is expressed as n-1 choose R. For example, if we need to choose all 2 items from our remaining set of B, C, and D, we are simply calculating 3 choose 2. This gives us exactly 3 possible groups. Bringing it all together, we are now combining the 2 cases. Logically, every single possible subset either contains the star or it simply doesn't. These 2 paths perfectly cover every possibility. They are exhaustive and mutually exclusive. Therefore, our grand equation is formed. N choose R equals n-1 choose R-1 plus n-1 choose R. We can easily verify this for our earlier example of 4 choose 2. 4 choose 2 is equal to 3 choose 1, which is the star in case, plus 3 choose 2, which is the star out case. Since both of those smaller combinations happen to equal 3, 3 plus 3 beautifully equals 6. This beautiful recursive pattern leads us gracefully into building Pascal's triangle. We can arrange all our combinations by row n and position r, with both starting from 0. At the very top, for row n equals 0, we simply have 0 choose 0. Moving down to row n equals 1, we have 1 choose 0 and 1 choose 1. The next row, n equals 2, gently holds 2 choose 0, 2 choose 1, and 2 choose 2. In row n equals 3, we find 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Finally, row n equals 4 contains 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Let us now look at Pascal's triangle with values. There is a magical property hidden right here. Each entry is exactly the sum of the 2 entries directly above it. For row n equals 0, we just have the number 1. The total sum of this row is 1. In row n equals 1, we have 1 and 1, which sum to 2. Row n equals 2 gives us 1, 2, and 1, adding up to 4. Row n equals 3 features 1, 3, 3, and 1, which total 8. And our familiar row n equals 4 reveals 1, 4, 6, 4, and 1, which perfectly total 16. Just as we saw earlier, 4 choose 2 is the exact sum of 3 choose 1 and 3 choose 2, because 3 plus 3 equals 6. And notice the final sums. The row sums always equal 2 to the power of n. We can truly see these identities in action within the triangle itself. The triangle visually encodes several identities we have already proved together. For instance, the addition rule formula, where n choose r equals n-1 choose r-1 plus n-1 choose r, is seen perfectly when 4 choose 2 equals 3 plus 3, or 6. The symmetry formula, where n choose r equals n choose n minus r, is beautifully mirrored when 4 choose 1 equals 4 choose 3, both resulting in the number 4. The boundary formula shows us that n choose 0 and n choose n always equal 1, just like 4 choose 0 and 4 choose 4. Lastly, the row sum formula demonstrates that adding all combinations in a row equals 2 to the power of n, just as 1 plus 4 plus 6 plus 4 plus 1 equals 16, which is exactly 2 to the 4th power.
Every single row of Pascal's triangle demonstrates all 4 of these beautiful identities simultaneously. This brings us beautifully to Part 5, Summary. Let us take a quiet moment to review our summary of key ideas. Our main formula is n choose r equals n factorial divided by the product of r factorial and n minus r factorial. We derived this directly from permutations, where n choose r equals n pr divided by r factorial, mathematically dividing out those extra r factorial arrangements. We learned about symmetry, where n choose r equals n choose n minus r, meaning that choosing items to keep is the exact same as choosing items to leave behind. We explored Pascal's identity, stating that n choose r equals n minus 1 choose r minus 1 plus n minus 1 choose r. And finally, we discovered that the total subsets of a group can be found by summing all combinations from 0 to n, which will always equal 2 to the power of n. I am so very grateful for your kind support. It truly means the world to me. Please consider liking, sharing, and subscribing to join our gentle community, and I would truly love to hear your wonderful thoughts in the comments below.